You are probably familiar with waves. The simplest wave you can think of has the shape depicted here on the top left. This will be a light wave, in particular, as you might expect by now, moving consequently at the speed of light, which is 1 light second per second. The distance between two crests is called the wavelength, and we will use the Greek letter lambda for it. We can represent this wave on our space-time diagram by plotting the path of all crests of it. Since each one of them travels at the speed of the wave, which is 1, we will have lines parallel to our r-axis, separated by a distance lambda horizontally. The vertical separation will be the time, called period and denoted by t, between two consecutive crests passing by a particular location. Take the position x equal to 0, for example. In our units, the wavelength and period will be given by the same number. We now perform our contraction expansion as usual by a factor of alpha, which we take to be 1/2 as usual. In the contraction along R, points on the green lines end up again on the same green line, so the pattern will not change due to this part of the transformation. The expansion, however, will be quite noticeable, as you can see. This part gives rise to a change in the period and wavelength by a factor of 2. We will call t prime and lambda prime at these two new values respectively. We will then have that t prime is 1 over alpha times t, and lambda prime is 1 over alpha times lambda. If we now define the temporal frequency ft as the number of oscillations per second, which is 1 over the period, and the spatial frequency fs as the number of oscillations per light second, which is 1 over lambda, we get the law for the transformation of frequencies. They both get multiplied by the contraction factor alpha. A wave moving in the opposite direction will have frequencies increased by a factor of 1 over alpha. Think about this to verify you understand the point of this video.